and I'm going to start the lecture today. So as we were discussing last time, or as I was describing last time, we were basically looking at wireless communication systems, multiple antenna wireless communication systems. So what I would like to do is I would like to continue with the discussion that we were doing last time, and basically go on to some other aspects of multiple antenna systems. So what we were doing last time is, if I have to remind all of you, we were looking at the bit error rate of a antenna wireless communication system, right? And therefore what we said was the following thing. We said first we said that the SNR, considering a two antenna system, considering two receive antennas, we have SNR equals norm of h bar square times P over sigma square. This is the SNR, this is the SNR after maximum ratio combining. Right, this is the this is the SNR after maximum ratio combining. Now what so other thing that and this norm h square, this magnet norm h square, this is equal to magnitude h1 square plus magnitude h2 square, right? This is equal to magnitude h1 square plus magnitude of h2 square, and denoting, and this is therefore equal to, I can write this as G1 plus G1 plus G2, where G1 equals magnitude h1 square and G2 equals magnitude h2, G2 equals magnitude h2 square. And therefore the SNR, the instantaneous SNR is a function of the channel gains. This can be written as SNR equals G1 plus G2 times P over sigma square, right? So this is what we said last time. So SNR is equal to G1 plus G2 times P over sigma square. Therefore the instantaneous error rate, bit error rate, that is Q of square root of SNR. So this is Q of bit error rate equals Q of square root of SNR. So this is equal to Q of square root of SNR, which is equal to, in this case, that is equal to Q of square root of 1 plus 2 to E over sigma square. So Q of square root of SNR is Q of square root of G1 plus G2 times E over sigma square. Also, we know the approximation for the Q function. The approximation for the Q function. Can someone tell me what is the approximation for the Q function? Q of x is approximately. Can someone tell me what is the approximation? What is the approximation for the Q function? Can someone tell me what is the approximation we use for the Q function? Anyone, can you respond via the chat window? What is the approximation that we use for the Q function? Yes, correct. I'm getting the answer from GCT. The approximation that we use for the Q function, that is U of x approximately equal to half e to the power of minus half x square. So this is the approximation that we use for the Q function. That is correct. So the approximation for the Q function is half e to the power of minus half x square. Therefore this Q of square root of g1 plus g2, using this approximation for the function, if I use the approximation for the Q function, this can be written as, you can see using this approximation, this is approximately equal to half e to the power of minus half e over sigma square into g1 plus. Therefore, using the Q function approximation, that is Qx equals half e to the power of minus half x square. Right, using the approximation for the Q function, that is Qx equal to half e to the power of minus half x square. I can write Q of square root of g1 plus g2 p over sigma square as half e to the power of minus half p over sigma square g1 plus g. Okay. Now this has to be averaged over the distribution of G1, G2, because G1, G2, these are random variables. Everyone can see this G1, G2, this channel gains G1, G2, these are random variables. These are random variables. Therefore, we have to average over the distribution of G1 and G2. Now, can someone tell me what is the distribution of G1? My question is, what is f of G1 distribution of, that is correct. So I'm getting the answer again from GCT. The distribution f of G1, that is exponential, very good, e power minus G1. How about f of G2? What is the distribution of G2? F of G2 equals, what is the distribution of G2? What is the distribution of G2? Distribution of G2 is e to the power of minus G2, KNMU, that is responding, GIT is also responding, e to the power of minus G2. Very good, very good. Therefore, what is the joint distribution? Now my question is, what is what is the joint distribution of G1, G2? Again, we also did this, correct? The joint distribution of G1, G2 is nothing but it is the multiplication of the distribution of G1 and G2 because G1 and G2 are independent. So since G1 and G2, therefore K and MU, all of them are replying correctly, that is correct. Since G1 comma G2 are independent random variables, the joint equals product since G1 and G2 are independent random variables, joint distribution is equal to the product of the individual random variables. Therefore, I have f of G1 comma G2 equals f of G1 into f of G2 equals e to the power of minus G1 into e to the power of minus G2 equals e to the power of minus G1 plus. This is the random distribution. This is the joint distribution of the channel gains G1 and G2. Here basically we are assuming that the channel gains G1 and G2 are independent. Let me remind you once again what G1 and G2 are. These are the two antennas and this is the transmit antenna. Then I have H1 is a coefficient corresponding to this and H2 is this coefficient. E1 equals magnitude H1 square, G2 equals magnitude H2 square. So G1 equals magnitude H1 square, G2 equals magnitude H2 square. Therefore now what we have to do is basically we have to average this. We have to average this function. Let me remind all of you, we have to average this function which is a function of G1, G2 over the distribution, over the joint distribution of G1, G2. Therefore the average bit error rate, therefore the average bit error rate therefore the average bit error rate equals R e to the power of minus p over 2 sigma square G1 plus G2 times e to the power of minus G1 plus G2 into Pg1 into Pg. So what am I doing? This is the bit error rate as a function of, everyone can see, this is basically the bit error rate. This is basically the bit error rate as a function of G1 plus G2. I am multiplying the distribution of, I am multiplying this with respect to the distribution of G1 G2. I am multiplying this with respect to the distribution of G1 G2 and I am integrating over G1 G2. Limits of G1 G2 are from 0 to infinity. Therefore I am computing the average of this function over basically the distribution of the joint distribution of the gains G1 G2, right? And we had also evaluated this. This can also be written as integral 0 to infinity, integral 0 to infinity I'll take the factor of half outside. This is e to the power of minus p by 2 sigma square g1 times e to the power of minus p by 2 sigma square into g2 e to the power of minus g1 e to the power of minus g2 pg1 pg2 equal to half 0 to infinity. Now collecting the terms, look at this, this is the terms, I'm going to collect the terms corresponding to G1 and collect the terms corresponding to G2. So these two terms correspond to G1 while these two terms correspond to G2. Therefore collecting the terms corresponding to G1 and G2, you can see this can be written as e to the power of minus G1 1 plus P over 2 sigma square into e to the power of minus g2 into 1 plus e over 2 sigma square dg1 into dg. So this is what it finally reduces to, half integral 0 to infinity, integral 0 to infinity. So the first integral here is over g1, second integral is with respect to 2, correct? And therefore this is equal to, now you can see this is the product of two separate functions. This is the product of two functions, one with respect to g1, one with respect to g1. So this is also separable. Therefore this is, in that sense, this is separable. Why is this separable? Because this splits into the product of two functions, one with respect to g1, another with respect to g2. Therefore this can be separated into two independent integrals. Therefore this is equal to, this is actually equal to half 0 to infinity e to the power of minus g1 1 plus e over 2 sigma square dg1 into 0 to infinity e to the power of minus g2 1 plus e over 2 sigma square d2, right? So it splits into two integrals because this is a product of two functions. One depends only on g1, one depends only on g2. Therefore it splits into the product of two integrals. Now can someone help me evaluate what is this component? So my question is, basically my question is, what is integral 0 to infinity e to the power of minus g1 e to the power of minus g1 into 1 plus p over 2 sigma square dg1. Now if you look at this, this is of the form integral 0 to infinity e to the power of minus ax dx. This is equal to integral e to the power of minus ax minus e to the power of ax divided by a between 0 to infinity, which is equal to 1 by a. That is correct. I am getting the answer from several colleges, GCT, UIET and VCAP. This is simply equal to, this integral is simply equal to 1 over 1 plus e by 2 sigma square. Very good. Very good. Very good. Several colleges have responded. Very good. How about integral 0 to infinity e to the power of minus g2 1 plus E over 2 sigma square Eg2, and everyone can see that is also the same. Correct. Very good, very good, very good. Correct. 1 plus E divided by 2 sigma square. Very good. Therefore, now substituting this, what I get is average bit error rate. Average bit error rate equals half 1 by 1 plus E over 2 sigma square whole square. So the average bit error rate is basically 1 over and right 1 over half times 1 over 1 plus P over sigma square whole square. Now P over sigma square, we are also calling this as SNR. P over sigma square is also equals SNR, that is transmitted power to the noise power at the receiver. This is also calling SNR, or more appropriately this is average SNR, right? So this is equal to half 1 over 1 plus half SNR whole square. At high SNR, what is the approximation? At high SNR, what will this reduce to? Can someone tell me what is this equal to at high SNR? What is the approximation? What is the high approximation at high SNR? What is the approximation at high SNR? Correct. At high SNR, this will become, look at this, at high SNR, I have 1 plus half SNR. So 1 is small compared to half SNR. So at high SNR, this is approximately equal to half into 1 over half SNR whole square equals half over 1 plus half SNR whole square, which is equal to 2 divided by SNR square. So at high SNR, this is basically equal to, correct, I am getting answer from PhD. Several people have replied, several colleges have replied, UIET also has replied. That is basically 2 divided by SNR square. That is 2 divided by SNR square. At high SNR, this is, yeah, GIT is also replying, this is at high SNR, the approximation is 2 divided by SNR square. At high SNR, at high SNR. So this is approximation at high SNR. This is the approximation at high SNR. Let me write it down clearly again. Therefore, at high SNR, at high SNR, will be so 2 antennas equals 2 over SNR square. Now let us go back again to calculate. See, similar. Everyone remembers we calculated what is the SNR required for AWGN and also fading channel with a single antenna at 10 to the power of -6 bit error rate. Now let us calculate with two antennas what is the SNR required. So my question to all of you is the following: with two antennas, in this two antenna system, what is SNR required for BR equals 10 to the power of 6. In two antenna system, what is the SNR required for bit error rate equals 10 to the power of minus 6. In a two antenna system, what is the SNR required? And I'm asking for SNR in dB. Please give the SNR in, I have to say SNR in dB. What is the SNR in dB? So my question is, what is the SNR in dB required for a bit error rate of 10 to the power of minus 6? What is the SNR required for SNR required? I'm getting the correct answer from GCT, PSGCT. The answer is, it's correct. It is 2 by, so we get basically 2 by SNR square equals 10 to the power of minus 6. Therefore, SNR equals, what is SNR? SNR equals 2 divided by 10 to the power of minus 6 square root, that is 2 divided by 10 to the power of minus 6 square root, right, which is basically equal to 31.5. So now 10 log 10 SNR, to find dB SNR I have to perform 10 log 10 SNR, which is equal to 31.5 dB. That is correct. Several colleges are applying, that is correct. To find the dB SNR, that is 10 log 10 of SNR. SNR is equal to square root of 2 over 10 to the power of minus 6, which is equal to, you can also write it as 1.414 into 10 to the power of 3, right, because square root of 2 is 1.414, right, into 10 to the power of 3. Therefore, required SNR in dB is 31.5. Now basically, to summarize the discussion so far, let us go through the values we computed once. See, we looked at AWGN. In AWGN, what is the SNR required for 10 to the power of minus 6? Does anyone remember what is the SNR required in AWGN? What is the SNR required in AWGN? SNR required in AWGN is 14 dB, and the SNR decreases as exponential, bit error rate decreases as e to the power of, in a fading channel with one antenna, that is in a single antenna relay fading channel, what is the SNR in relay channel with one antenna? With one antenna, we saw there is a drastic increase in the SNR that is required. Can someone remember what is the SNR that is required in a relay fading channel with a single antenna? That is 60 dB. Because bit error rate decreases only as 1 over SNR. Everyone remember that? Because bit error rate decreases only as 1 over SNR. However, now with multiple antennas, with two antennas, what happens to SNR? SNR has again come down, required SNR has come down to 31.5 dB, because bit error rate, you can see, is decreasing as 1 over SNR square. You can see the bit error rate has decreased From 1 over SNR, bit error rate has become 1 over SNR square. Therefore, the SNR that is required has decreased significantly. So, the transmit power that is required has decreased significantly. So, that is the advantage of having multiple antennas. So, with multiple antennas, so the advantage of multiple antennas, let me summarize the advantage of multiple antennas. What is the advantage of having multiple antennas? Can someone tell me what is the advantage of having multiple antennas? Can someone summarize what is the advantage of having multiple antennas? Can someone summarize what is the advantage of having multiple antennas? What is the advantage of having multiple antennas? Yeah, I'm getting the answer from GIT. That is, the advantage of multiple antennas is that the required SNR is reduced, so that transmit power, that is overall transmitting power, the transmit SNR, right, correct. So the SNR required is lower, so the amount of transmitted power required is lower to achieve the same bit error rate, that is 10 to the power of minus 6. So the advantage of multiple antennas is basically the required SNR is lower to achieve the same bit error rate. Therefore, multiple antennas are able to combat the problem, are able to overcome the problem of fading in wireless communication system. Therefore, we are able to overcome the problem of fading in the fading in wireless. Therefore, by using these multiple antennas, we are able to decrease the bit error rate significantly. Right? We are able to decrease the bit error rate significantly, or for the same bit error rate required, we are able to decrease the transmitted SNR significantly. This is also known as diversity. This is also known as, using these multiple antennas, this is also known as diversity. This is also known as diversity of communication. Diversity means basically using multiple antennas or multiple modes to receive signals to basically decrease the bit error rate of the communication system. This is also known as the diversity of the system. So diversity, so property of diversity is basically diversity. Instead of one receive antenna, we are now using two receive antennas. Thereby, by increasing the number of antennas, we are able to decrease the bit error rate of the wireless communication system. This property, this is also known as diversity. By increasing the diversity, we are able to increase the bit error rate of the wireless communication system. Okay, so far okay. By increasing the diversity, we are able to decrease the bit error rate of the wireless communication system. I'm getting a question that as the number of antennas increases, transmit power keeps decreasing further. That is correct. As the number of antennas increases, the transmit power keeps decreasing. In fact, you can see now let us do it for the general case of L receive antennas. For the general case of L receive antennas, for L receive antennas, that is, I have a communication system which looks this is the receiver, this is the transmitter, and I have antenna 1 coefficient H1, antenna 2 coefficient H2, so on, antenna L coefficient HL. Therefore, in this system I have L received signals. I have Y1 equals H1X plus N1. I have Y2 equals X plus N2, so on so forth. I have YL equals HLX plus NL. Right, so I have a L receive antenna system. Now I can write this as a vector. I can write this as a vector with, basically, if I can make this, you can see where I am drawing the brackets. So I am making a vector out of these things. So I basically have my system model is now y bar equals h bar x plus n bar. This is the same as previous, but instead of two antennas, now I have L antennas. Instead of two antennas, now h bar, instead of two antennas, I have L antennas. So now instead of two antennas, I have L antennas. Therefore, can someone tell me now how should I process the received signals Y1, Y2, YL in this system? Can now, using the intuition for two antennas, can someone tell me how should I process? My question now is, how should I process Y1, Y2, YL? We already did it for two antennas. How should I process the received signals Y1, Y2, YL in this system? How should I process Y1, Y2, YL in this system? Can someone answer this question? How should I process the received signals Y1, Y2, YL in this system? Can someone answer this question? How should I process Y1, Y2, YL in this system? We have to perform a weighted combination of the outputs. Now can someone tell me what are the weights to perform the weighted combination of the outputs? Can someone tell me what are the weights? That is correct. We have to perform the weighted combination of outputs. Therefore, we have to perform W1 conjugate Y1 plus W2 W2 conjugate Y2 plus WL conjugate YL. We have to perform a weighted combination of the outputs. Can someone now tell me what is the set of weights that will maximize the SNR at the output? What is the combination of weights that will maximize the SNR at the output? So we perform a weighted combination of the outputs. Can someone tell me how should we choose the weights? What are the weights in this weighted combination of the outputs? Can you look at the what we did? Can we look at what we did previously? So my question is, what are the optimal combining weights? What are the optimal combining? What are the optimal combining weights? Can someone tell me what are the optimal combining weights? GCT is giving me the answer, that is we have to use a maximal ratio combiner. Correct, we have to use the maximal ratio combiner. What is the maximal ratio combiner? We have to use, correct, very good. We have to use maximal ratio combining. Correct, that is MRC. What is the maximal ratio combiner? Can you tell me H bar divided by norm H bar? VCAP is also coming with the correct answer. That is very good. H bar divided by norm H bar. So the maximal ratio combiner is H bar divided by norm H bar. That is equal to 1 by norm H bar times H1, H2, so on up to HL. This is the maximal ratio combining vector. That is the vector W bar equals H bar divided by norm H, that is H1, H2, HL divided by norm H, where norm H is equal to norm H bar is equal to under root of magnitude H1 square plus magnitude H2 square plus magnitude HL magnitude H2 square plus magnitude HL square. Fine. This is norm H. Therefore W1, for example, W1 you can see W1 equals H1 divided by norm H bar. W2 equals H2 divided by norm H bar. So on, WL equals HL divided by norm H bar. And therefore the combining is W1 conjugate Y1, which means H1 conjugate divided by norm H bar into Y1 plus W2 conjugate, that is H2 conjugate divided by norm H bar into Y2 plus plus HL conjugate divided by norm H bar into YL. That is H1 conjugate divided by norm H bar into Y1 plus H2 conjugate divided by norm H bar into Y2 plus HL conjugate divided by norm H bar into YL. That is basically the optimal combining at the receiver. This is also the maximal ratio combiner. This is also the maximal ratio combining. This is also termed as the maximal is also termed as maximal ratio combining, but now we have generalized it to L antennas. We have generalized, previously we had considered only two antennas. We have now generalized to L. We have now generalized to L antennas. Now therefore in this maximal ratio combiner, what is the SNR at the receiver? Can someone tell me what is, if I use this maximal ratio combiner, what is the SNR at the receiver? SNR at the receiver. What is the SNR at the receiver when I use this maximal ratio combiner? Can someone tell me what is the SNR at the receiver when I use this maximal ratio combiner? Norm H square into P divided by sigma square. That is correct. SNR at the receiver is equal to norm H bar square into P divided by sigma square. SNR is equal to norm H bar square into P divided. I am asking for SNR at the receiver. SNR at receiver, that is norm H square into E divided by sigma square, which is equal to, that is equal to, everyone can see this is norm H square is nothing but magnitude H1 square plus magnitude H2 square plus so on magnitude HL square P divided by sigma square equals E1 plus G2 plus GL into P divided by sigma square, where G1 equals magnitude H1 square, G2 equals magnitude H2 square, GL equals magnitude HL square. Okay. Therefore now can someone tell me what is the bit error rate as a function of the channel gains? My question is, what is the instantaneous bit error rate? What is the current bit error rate? Not the average bit error rate. What is the current bit error rate as a function of these channel gains? What is the current bit error rate as a function of channel gains? Q under root of SNR. Very good, very good. GCT has replied, KNM, UPSG, several colleges have replied. Q, GIT is also replied, Q under root of SNR. That is Q square root of times P of sigma square. This is the current SNR as a function of channel gain. This is also known as the instantaneous SNR. This is also known as the instantaneous. This is also known as the instantaneous SNR at the receiver. Very good. So now based on this instantaneous SNR at the receiver, what is the approximation for the Q function? What is the approximation for the Q function? So this is equal to, very good, half e to the power of Q function Q of x is half e to the power of minus half x square. Therefore, this is equal to this instantaneous SNR approximately equal to half e to the power of minus half e over sigma square into G1 plus Now can someone tell me if the average channel, if the instantaneous, what is the distribution of G1, G2, joint distribution of G1, G2, GL, if the gains G1, G2, GL are independent? What is the joint distribution of, my question is, if G1, G2, GL are independent, what is joint distribution correct, joint distribution of G1, G2, GL is nothing but product of the individual distributions, that is e to the power of minus 1, e to the power of minus G2, that is correct. I am getting the answer f of G1, f of G2 into f of GL, that is e to the power of minus GL, which is equal to e to the power of minus G1 plus G2 plus, okay. So alright, so basically come to here, I think we have completed basically, so today's lecture, because we are coming close to the end of this thing, let us stop it here because I am running short of time, it is on, and what we will do is we will continue from this point in the next lecture. So we have come to, basically we have derived two relations. One is we have derived the joint distribution of the channel gains G1, G2, GL, and also the instantaneous bit error rate in a multiple antenna system, a system with L antennas. In the next lecture we will carry this derivation forward. This procedure we will carry it forward in the next lecture. Thank you. Thank you very much.